Okay, picture this, a gigantic cargo ship, basically a floating city made of steel just gliding across the ocean. Its engines, they're the size of a house, and its fuel tanks could literally swallow a bus whole. Now, everything on that ship depends on knowing exactly how much fuel, oil, and water it has on board. But how do you even begin to measure that? Let's get into it.
Right? That's the big question. When you've got a tank that's dozens of feet deep, holding thousands and thousands of gallons of sloshing liquid, you can't just pop the cap and take a quick look inside. It's a massive engineering puzzle, and the solution is, well, it's surprisingly clever. I mean, it seems obvious, but it's not just impractical. A lot of the time, it's straight up impossible. Many of these tanks are totally sealed, some are under pressure, and some hold pretty hazardous stuff. You just can't open them up. So to see inside, engineers had to think way outside the box and figure out a way to measure without actually looking. And here's the secret. The trick isn't to measure the level of the liquid itself. Nope. The trick is to measure something else that's directly connected to it. This whole approach is the absolute key to modern industrial measurement, and it's what keeps these massive ships running safely and smoothly. And this idea has a name. It's called Differential Level Measurement. So instead of trying to measure the height of the liquid, you measure a property like pressure, or maybe even how long it takes a signal to travel. And from that data, you can perfectly calculate or, infer the level. It's a brilliant workaround to a really tough problem. And this really shows you the difference in thinking, right? On the left, you've got direct measurement. Super simple, a ruler, a dipstick, but it's also really limited. And on the right, you have the inferential method. It's indirect, yeah, but it's way more powerful and versatile. It's kind of like the difference between reading an old paper map and using live GPS on your phone. So how exactly do they pull this off? Well, it turns out there isn't just one magic bullet. There are actually several really ingenious methods, and each one has its own strengths. We're going to take a look at the four most common ones you'll find on ships today. First up, we've got the real workhorse of the fleet, the hydrostatic sensor. The principle here is beautifully simple. The deeper the liquid, the heavier that column of fluid is, and so the greater the pressure at the bottom. By putting a sensor right at the bottom of the tank and measuring that pressure, you know exactly how much liquid is sitting on top of it. All right, method number 2, and this one is super cool. It's called a bubbler system. You have a tube that goes all the way to the bottom of the tank, and it just lets out a constant, tiny stream of air bubbles. Now, to make those bubbles, the air has to push against the weight of all the liquid above it. The amount of pressure it takes to do that, what they call the back pressure, tells you exactly how high the liquid is. It's genius, really, because the sensor itself never even has to touch the fluid. Okay, our third method is all about timing. There's a sensor mounted at the very top of the tank, and it sends out a quick pulse. This could be a high-frequency sound wave that's ultrasonic, or a radio wave, which is radar. This pulse shoots down through the empty space inside the tank. And then that pulse hits the surface of the liquid and bounces right back up, just like an echo in a cave. The sensor measures with incredible precision the time it took for that round trip. Since we know exactly how fast the signal travels, the system can instantly calculate the distance to the liquid, and boom, you know the level. And it does it all without ever touching the liquid. And finally, our fourth method uses electricity. A capacitance sensor basically has two electrodes. As a liquid like fuel or oil rises up between them, it actually changes the electrical properties of that circuit. The system just has to measure this change in what's called capacitance to figure out the level. For the right kind of fluids, this method is incredibly precise. So we've seen the what, but let's just take a quick peek at the how. Let's zoom in on that first method we talked about, the hydrostatic sensor, and see what's actually going on inside that little metal device. Think of it like a four-step chain reaction. First, there's a flexible metal disc at the front, the diaphragm, that feels the pressure from the liquid and flexes inward. This push gets transferred to a special incompressible oil to a part called the transducer. Now, the transducer is where the magic happens. It converts that physical force into a tiny electrical signal. And finally, an electronics module takes that weak signal, boosts it, and turns it into a standard format that the ship's main computer can easily read and understand. Now look, this isn't just some fascinating piece of tech for the sake of it. It is absolutely critical. Let's see where these invisible gauges are working 24/7 to keep the ship safe and running like it should. Honestly, they're everywhere. They are constantly monitoring the fuel tanks that feed the massive main engine. They're in the lube oil sump, making sure that engine doesn't seize up.
They're in the enormous ballast tanks that keep the entire ship stable in the water. They're even in the cooling water systems to prevent overheating. Without these reliable measurements, a modern ship just couldn't operate. Period. So we've looked at 4 totally different ways to do the same job, and they all work. But this brings up a classic engineering question. If you've got multiple solutions, how do you pick which one to use?
Well, that's the thing, isn't it? There is no single best method. The right choice always depends on the specific job you're trying to do. It's all about weighing the pros and cons of each technology for that particular application.
And it really comes down to understanding these trade-offs. The hydrostatic sensor is super reliable, but its accuracy can get thrown off if the liquid's density changes, say with temperature. The bubbler is cheap and keeps the sensor clean, but hey, that tube can get clogged. Radar is great, no moving parts, but it costs more and can get confused by pipes or other things inside the tank. And capacitance? It's really accurate, but you have to calibrate it carefully for every single type of fluid. It is always a balancing act to pick the right tool for the job. And that really brings us to what's next. These aren't just simple gauges anymore. They are smart sensors, feeding crucial data points to the ship's brain. As we move closer and closer to a future of autonomous shipping with fewer and fewer people on board, these silent, tireless, reliable sensors, they're going to become the ship's essential eyes and ears, constantly reporting on its vital signs. And how we learn to trust and use that data, well, that's going to define the next generation of life at sea.